Okay, so related to that, we want to talk about plate buckling, basically the buckling of these upper surfaces that are made of the skins and the stringers, and how that is related to the spar spacing. It's pretty dominantly related to the spar spacing. So here I have a kind of again a typical cross section. Um, we have a spar on the right and the left, skins on the top and the bottom, and I've put some stringers arbitrarily on the top and bottom surfaces. So the idea here is we want to look at the buckling of that top surface, assuming the lift is up or whatever it is that would cause it to push that into compression. And so down below, you can see we have the applied distributed force. This again comes from the lift, okay, where it's N, and this is going to be force per length. Okay, it's distributed along that edge. On the right and left sides of that panel, we have spars typically, and on the front and back of the panels, we are going to have ribs. Okay, so A is again the rib spacing, and B will be our spar spacing. So this distance here is B. Okay. So the way this works, again, is the critical buckling load for this system here. Again, that's going to be force per length, is this aspect ratio mode parameter K pi squared times D, which is the plate stiffness factor, over B squared. Okay. So D is the plate stiffness factor. When you do plate theory, it's typically defined as E T cubed over 12 1 minus nu squared. But as we've talked about in the previous classes, this quantity here can be thought of for a plate. That is the I of the plate over or per the length, I through B. So for us, I prefer thinking of this as E over 1 minus Poisson's ratio squared. So that's a quantity that's just comes from the fact that the in-plane response is plane stress. That's the material constants times I for the section over B. And I'll put a little subscript here to meaning that that's the I of the plate. All right. Okay. B is the width of the plate, and then this parameter K is equal to M is a mode shape, A over B plus B over M, A quantity squared, where M is the buckling mode. Now remember, with the buckling mode, we can actually, depending upon the aspect ratio, we could get a first mode buckling, or we could also get, if we have a bigger aspect ratio, it's so hard to draw straight lines on this stupid thing. You could also get like a second mode. So this one would be M equals 1. Here's M equals 2. And you get M equals 3, so on and so forth. And then obviously A over B, that's the plate length versus the plate width. That's the aspect ratio. Now, if you remember, when you look at this and you plot it out, what you get if we plot on the x-axis the aspect ratio A over B, and we plot K on the y-axis, what you get are these curves depending upon the mode, and the K is going to be the lowest value, right? So basically up till, I think it's square root of 2, but I'm not exactly sure, you're going to have mode 1, and then you're going to get mode 2, and then mode 3, and then mode 4. But one thing to notice that once you get an aspect ratio greater than 1:1, K is pretty close to always being 4. Okay. So the big thing is, yes, the aspect ratio can somewhat control K, but really not that much. So if we go back and look at this equation, what dominates plate buckling? Well, obviously it's going to be the plate stiffness, D. So the I of the plate. Okay. K, like I said, is kind of like always going to be 4, close to 4. And then the other big thing is B. So B and D right? And so B, again, is that spar spacing. So actually the rib spacing, A, doesn't have that much effect. It's mostly due to the spar spacing. Okay? All right. So that's how we compute the critical buckling load. And again, if you wanted to we need to compare that to the actual N in the plate system. Here, I'm going to draw this. So here I'm just kind of zooming in on some type of plate system, right? With plates and stringers in this case. Here is the neutral axis of the box section. And oh yeah, you know what? Let me just take a little pause. Let me emphasize it again. So when we're talking about I of the plate, we want to find I of this system here, okay? Where this is the neutral axis of the system of the top skin and the stringers, forgetting about the rest of the wing. That's what we want, okay? And this distance here is B. I should make that very clear, right? That's really what we're going to design. So we want to increase that IP as much as possible. Okay. Again, E and nu, we don't really have that much control because we're very often dealing with aluminum. All right. Okay, so that's how you would calculate the critical buckling load. Now, to figure out what's the actual load in that system, much like with the stringer, now we have to think about this in the context of the entire wing system because, right, we want to find out how much axial force is picked up by the rest of the structure versus this system here. So again, this is going to be B. I'm going to do this. What is N in the okay, not the critical one, but what is the N we actually see? So again, it's going to be the same thing. We are going to get that the force is equal to the change in the moment, just like we did for the stringer. That's over the rib span. Q, that's going to be Q of that whole top plate system, right? Over I, and this is I for the entire wing. Cross section, I should say. Okay? And N is going to equal, I'm sorry, I said N and I wrote M. So N, that is that force P over the width of the plate B. And so this is just going to give me, you can do it in 2 steps, or you could just, put it into this equation. It doesn't really matter. All right. And that's how you do it. Okay. So we have a design. We're going to calculate the critical buckling load. Then we will also calculate what is the load, distributed load N in the system we have. So we'll need the lift and all that sort of stuff. Compare those two. And if it does buckle, we could either increase IP, we could do that, or we could also increase B. B will have a dramatic effect on that. Okay? All right. Okay, so let's stop there, and then I'll do an example. I'll continue that same design.